Hey everyone, in this video we're going to look at some preparatory support material for Math 155 week number 2. Specifically we're going to address factor trees, what they are, what their usefulness is in mathematics. We're going to look at perfect squares. We're going to discuss reducing fractions to their smallest form, writing fractions as decimals, solving equations using division. And then we'll close out by defining what real numbers are and looking at rounding rules. It is likely this is going to be a fairly lengthy video. There's just so much material to cover in this one. So of course it goes without saying you can pause and come back as you please. But try to make sure, as I mentioned in the previous video, to get through this material before you start on the material that week for your Math 155 course. All right, without any further ado, I love that word, let's go ahead and get the show on the road. So here we're going to start out talking about factor trees, what they are. You probably already know what they are. You may have forgotten about them, but you probably already know what they are. And what they do is they allow for the identification in as far as we're concerned. There's a lot of things we can do with them, if you will, for identification of perfect squares. And before we get into those, let's talk about what a perfect square is. You know, perfect squares are a result of squaring a given number. You know, if you were to, let's just arbitrarily put something on here. Let's say the number 3, and we were to say the square root of it. Look at that number we get, 1.7302508. That would be what we'd call an irrational number. There's no discernible pattern. It just keeps repeating forever. But on the same hand, look what happens when we do the number 100. If we do number 100, what do we get? We get 10, no decimals. If we do the number 25, what do we get? We get 5, okay? Let's do the number 49. We do the number 49, we get 7. All of these numbers where we're getting just a single, if you will, integer value, no fractions, no decimals, those are called perfect squares. They're rare. They're unique. Most numbers are not perfect, okay? But perfect squares can help you, as you'll find out in your Math 155 course, deal with approximations and you know, actual solutions to radical type problems, problems using the radical symbol, using what some of us call the square root symbol, using the radical symbol. So let's just go ahead and talk about, if you will, for a couple of minutes, the idea of factor trees first. And I'm going to ahead and put up a blank sheet of paper under here, so we'll pull it up and work on it. Let's say we wanted to take the number 18 and we'll do the number 56 as well. And we wanted to break them, use a factor tree to break them down into their smaller factors. Remember, in the language of math, if we were to go 6 times 7 equals 42, 6 and 7 are what we call factors. In the language of math, because we're multiplying, the answer is called a product. But long story short, the name we give to values that we multiply together are called factors. So these are called factor trees. We want to break them down into their smaller components. And we're going to utilize something called prime numbers. Prime numbers. What are prime numbers? Well, let me just go ahead and write out the first 10 prime numbers for you. And there's not a lot of things I generally tell students to try to memorize in math, but I would try to memorize the first 10 prime numbers. It's amazing how often you utilize prime numbers. We can use them in simplifying fractions. You guys are going to be using them in your Math 155 course initially to deal with radical solutions. There's a lot of things we can do with them. Your first 10 are 2, 3, 5, 7, 11, 13, 17, 19, 23, and 29. And they go on forever, and that's an ugly 3. Having trouble with 3s this week. Okay, so those are your first 10 prime numbers. To keep this video under 2 hours, what makes a number prime? Well, let's just arbitrarily pick a couple of these numbers here. 3. If we were to make our factor tree, which is something we'll utilize later on for simplifying fractions, make a little T-chart. And basically I'm going to say, what numbers can I multiply to arrive at 3? Well, 1 and 3. Okay, how about 13? Well, the same thing. There's only 2 numbers I can multiply to get to 13. 19, same reality. In every case, the number only has 2 factors. Remember, numbers that we're multiplying to arrive at numbers are called factors. Well, prime numbers have exactly 2 factors, the number itself and 1. That's unique. Okay, that's unique. Prime numbers are kind of like prime beef. They're special, if you will. There's a deeper reason behind the name, but for our purposes, it works. Okay, these are prime numbers. A prime number only has two factors. There's only two numbers that you can multiply, or the opposite of multiplication is division, that you can divide into the number evenly, and that would be the number itself and 1. So we're going to use factor trees. We're going to take these two numbers and we're going to use factor trees to break them down into their smaller components. Specifically, we're going to break them into prime numbers. Okay, and we'll use those prime numbers to help us on the next part of this presentation, where we find the largest perfect square of numbers, which is something you'll use in your 155 course for solving radical problems, either approximations or actual solutions. Okay, so here what we're going to do is we're going to do this. We're basically going to make this little, they look like the roots of a tree. That's the best guess I can give you as to why we call them factor trees. And basically we're going to do this. We're going to say, okay, what two numbers can I multiply to get to 18? Well, there's a lot of numbers. We could do what? And remember, 1 is not a prime number. It used to be. The rules of math changed over the decades. It used to be considered a prime number. It's considered neither prime, and if a number's not prime, we say it's composite. 1 is considered neither composite nor prime. It's its own unique number. So we don't never a lot of folks would say we could go 1 times 18, but we're trying to list prime numbers. This is called a prime factorization tree. Okay, and 1 is not a prime number. So our smallest prime number is 2. Okay, it's the only even prime number as far as we know. All the rest of your prime numbers are odd, but don't confuse odd with being prime. The number 9 is an odd number, but you don't see 9 on here because there's more than two numbers you could multiply to get to 9. 9, you could go what? You could go 1 times 9, 3 times 3. The number 15 is not on here. 15 is an odd number. We could go 1 times 15, 3 times 5. 15 has 4 factors. A number that has 3 or more factors is called a composite number. A number that has exactly 2 factors is called a prime number. And then there's number 1, which is all by itself. Okay, we don't classify it as prime anymore, and it's definitely not a composite number. It's not composed of more than 2 factors. So we're looking for prime numbers. Well, there's a lot of them we could do here with 18. We could go, what, 2 times 9, 3 times 6. There's a lot of numbers we could do. Keep it simple. I'm always going to recommend it. You start with the smallest numbers and go large. Okay, if you have a preferred system you like to use, you're comfortable with it, it works, by all means use it. Here's what I'm always going to do. I'm basically going to always do this. I'm going to go, in this case, 2 times 9. I'm trying to break it into prime numbers. That number's already prime. I'm just going to put a circle around it. I'm done. 9 is not a prime number, so we keep going. 3 times 3. Well, both of those numbers are prime. Okay, both of those numbers are prime. So what have we done? We've broken 18 into prime numbers. 2 times 3 times 3 times 3. 2 times 3 is 6. 6 times 3 is 18. So we've broken it into prime numbers. Right now we're just concerned with breaking a number into prime numbers, factoring it to prime numbers, if you will. We'll use these sets of prime numbers on the next part to find the largest prime of some numbers. Again, so you can work on some radical type problems in your, literally, radical type problems in your Math 155 course. So let's do 16, or 16. Need some new contacts. 56. We could go, again, it ends with an even number, so 2 will go into it. We could go 2 times 28. 2 is prime, 28 is not. We could go 2 times 14. 2 is prime, 14 is not, so we could go 2 times 7. And now both of our bottom numbers are prime. So 56 in prime numbers would be 2 times 2 times 2 times 7. 2 times 2 is 4. 4 times 2 is 8. 8 times 7 is 56. You'll sometimes see this rewritten as 2 to the third times 7 as well. That's just basically saying, hey, there's 3 of those 2's. That's another way of writing that one. So that's a factor tree. Okay, that's what a factor tree does for us. That's its purpose. It allows us to take numbers and break them down into prime numbers. Your first 10 prime numbers there, again, 2, 3, 5, 7, 11, 13, 17, 19, 23, and 29. You can take those 10 prime numbers, and if I were to give you a number that had 800 digits in it, you could fairly quickly break it into its component prime factors. Okay, prime factors. All right, so let's move on from that. All right, and let's bring, oops, didn't mean to show that one yet. You didn't see that. You see nothing behind the curtain. All right. Here are your a list of perfect squares. Basically, 2 times 2 is 4, 3 times 3 is 9, 4 times 2 is 16, 2 to the second is 4, 3 to the second is 9. It's been a long day. 4 to the second is 16, 5 to the second is 25, 6 to the second, which is what? Shorthand for 6 times 6, 36, 7 to the second, shorthand for 7 times 7, 49, etc. These are your commonly known, it's kind of like the first 10 prime numbers, we commonly remember probably up to about 13. 13 squared is 169. These are your first, how many is this? This is 16 here. First 16 perfect squares. Do you need to memorize these? No. Do you probably want to have them available maybe in the front or back of your notebook? I would think so. They're going to aid you in dealing with the radical type problems in your Math 155 course. So I would definitely be aware of the idea of these. Okay. All right. So now let's get into it. Let's get over here and let's start. Finding, and what we want to do here, and we're going to use factorization trees for it. What we want to do is find the largest perfect square that divides into each of the following numbers. Okay, find the largest perfect square. Perfect squares again. 4, 9, 25. Those perfect squares. We want to find the largest ones that will multiply into these numbers. Why? Because it's something you're going to do in 155 to find precise or approximate solutions to radical type problems. Okay? All right, so this is simply a tool that we utilize. So I've got a couple sheets of blank paper here under this slide. So let's just go ahead and start with this, and I'll show you how to use it. We've already used 18 before. We used 18 and 56 on the previous slide to break them into prime numbers. We'll be switching back and forth on this one. Let's use 18. I want to find the largest, this is number 1 on our slide. We want to find the largest perfect square that goes into this number. So we're going to start out by breaking it into prime numbers. Okay, I guess I need to bring it down so you can see it on the camera. All right, we're going to go 2 times 9. Again, 2 is a prime number, 9 is not, so we're going to go 3 times 3. Fact is, let's just rewrite those first 10 prime numbers up top. So we'd have 2, 3, 5, 7, 11, 13, 17, 19, 23, 29. Those are our first 10 prime numbers. All right, so here we've broken 18 into prime numbers. And as your Math 155 instructor is going to tell you, when it comes to finding largest perfect squares, you want to look for pairs of numbers. Here you have 2 3s. Well, you can take those 2 3s and you can multiply them. And basically what you have found is that the largest square number, the largest perfect square, if you will, that will go into 18 is 9. Okay, and in your Math 155 class, you'll use that information, knowing that 9 is the largest perfect square that will go into 18 to give precise or approximation solutions to radical type problems. Okay, number 2, let's see, 500. Number 2 is 500. Okay, so we're going to take the number 500 and we're going to break it into prime numbers. We're going to take and break it into prime numbers. Well, again, we could go here. I'm going to start with 2 because it ends with an even number. So I'm going to use my prime numbers from left to right. It's just my habit. You don't have to do that. I could go 2 times 250. 2 is prime. 250 is not. I could keep doing that process. I could go 2 times 125. Okay. Let's see, what else could I do here? Let's see. 2 won't go into that, so let's try 3. Well, the rule for 3 is add our numbers together. 1 plus 2 is 3, plus 5 is 8. 3 won't go into 8, so we move on and try 5. So 5 will go into that what? Well, I think it's 25, but hopefully you know me in arithmetic by now. We're sometimes not on a first name basis. So what we can do here is go 125 divided by 5. 125 divided by 5 is indeed 25. 25 is not prime, so we keep going. 5 times 5. So what have we got here? Well, in this case here, we've identified 2 pairs. We have a set of 2s and we have a set of 5s. It doesn't matter which 2 5s you use. We'll just use these 2. So then we could take those two 2's, 2 times 2 is 4, and we could take those two 5's, 5 times 5 is 25, multiply those together, gives us 100. The largest perfect square that will go into 500 is 100. Okay, again, that information is going to come in handy when you're dealing with your radical solutions, solving radical problems, precise and approximated solutions. Okay, number 3, we have the number 375. Let's do that one. 375. Okay, so here we're going to take 375. Well, 375 does not end. It does not end with an even number, so 2 will not go into it. So we can't use that first prime number. We can't use this first prime number. How about 3? Will 3 go into this? Well, the rule for 3 is add your numbers together. The rule for 3 is add your numbers together. Let's see, 3 plus 7 is 10. 10 plus 5 is 15. Will 3 go into 15? Yes, then it'll go into this. If we pull out a calculator here, we're going to find out. Let's see here. 375 divided by 3 is 125. So 3 times 125. 3 is prime, so we're done with that. Here we had this one over here, so we know it's 5 times 25. Okay, 5 is prime number, but 25 is not, so we keep going. Okay, and then what do we have here? Well, we have a situation where we only have one, we can only come up with one pair. Okay, we can use these two 5s or those two 5s. Let's just use these two. 5 times 5 is 25, and basically what we found out is the largest perfect square, which is 25. Again, a perfect square would be something what? If we squared it, 20. Where was it here? 25. 25. We get a single digit. We get a single integer value. We do not get any decimals. Okay, that is a perfect square. So the largest perfect square that will go into 375 is 25. Again, this may seem like esoteric, just good to know information, but this is something you're going to utilize in Math 155 when you're dealing with those radicals in week 2. Okay. Next one is 242. 242. So we're going to do the same thing here. 242. This is question number 4. We're going to take and we're going to break it into prime numbers. Okay. So this one we could go, it ends with an even number, so we could go 2 times 121. And then, this is where you may have to break out a calculator. We find out, hey, that's 11 times 11. Okay, 11 times 11. All right, so we're done. So do we have any pairs? Yes, we do. We'll take those two numbers, 121, and we have just that quickly found out that the largest perfect square that will go into 242 is 121. And again, this is just knowledge for knowledge's sake, process for process sake. This is simply one step in a larger process, which we'll cover in 155. This is dealing with simplifying those, simplifying actually is what you're doing, those radical type problems. You know, the problems that are going to have, you know, like 25 plus, you know, something like that. Okay, that's the type of problem I'm talking about that you're going to deal with in your 155 course. Knowing these perfect squares are going to help you do that. Okay, what was the next one? Next one was 56. All right, so let's deal with 56 here. We'll take this sheet of paper and we'll take and rewrite our prime numbers at the top of it again. First 10, 2, 3, 5, 7, 11, 13, 17, 19, 23, 29. They go on forever. So we had, what did we say, 56? So number 5 was 56. We're going to take each of these numbers, break them into prime numbers. So here we could go, what? It ends with an even number. So we could go 2 times 28. 2 is prime, 28 is not. We keep going. 2 times 14. 2 is prime, 14 is not. We keep going. We get 7. Okay, so we're done. Both of our bottom numbers are prime. Do we have any pairs of prime numbers? We do. Okay, we're looking for pairs is what we're looking for. Okay, 2 times 2 is 4. So basically we have found that the largest perfect square that will go into 56 is 4. And that's all we're looking for in this case. We're looking for the large, we need to break them into prime numbers, but then we need to take the pairs of the prime numbers and factor them. Remember, factor means multiply in math. Okay, if I tell you to factor 2 and 3, you should say 6. Okay, factor, that language of math. Factor means to multiply. All right, so if I were to show you the fact, we're looking for the pairs of factors, and then once we factor them, multiply them, it gives us our largest perfect square. Again, this is something we will use to simplify radical type problems. All right, number 6 was what? Number 6 was 96. Okay, let's do number 6 here. So 96. We're going to take 96 and we're going to break it into prime numbers. Okay, it ends with 2, so we can go 2 times 48. That's a prime number. 48 is not. We can go 2 times 24. 2 is prime. 24 is not. We keep going. 2 times 12. Okay, 2 is prime. 12 is not. We can go 2 times 6. 2 is prime. 6 is not. And lastly, we can do 2 times 3. Okay, so once our bottom numbers are prime, what do? Well, we're going to look for pairs. Let's see. We've got a pair of 2's there. I've got another pair of 2's there. So we've got 2 pairs of 2. So we can go 2 times 2 is 4. And then 2 times 2 is 4. And then we'll multiply these together, and it gives us 16. And here we have figured out that 16 is the largest perfect square that will go into 96, that will factor into 96. 16 is our largest perfect square that will go into 96. And I ran out of page on this one, so let's just turn it over and do it on the back. I'll rewrite these prime numbers again. 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, and go on forever. So number 7 on our list of problems to do was 320. Let's find the largest perfect square that will go into 320, if you will. Ends with an even number, so we know 2 will go into it. 2 times 160. And again, you may have to break out a calculator. You may have to go, okay, well, let's see. 320 divided by 2, 160. Okay, and that's okay. It's no big deal. So that's a prime number. That's not. Here we could go 2 times 80. Okay, 80 is not prime. 2 times 40. We just keep going. 2 times 20. Okay, 2 times 10. And 2 times 5. Okay, and what have we got here? Well, let's see. Let's look for pairs of primes. So we got 2 primes. We got 2 primes. We have 2 primes. So for 320, okay, we could say perfect squares. It's 2 times 2, which is what? 4. And then we got another pair of them. 2 times 2, which is 4. And then we got another pair of them. 2 times 2 is 4. And then we'll multiply these together. 4 times 4 is 16. And then 4 times 16 is 64. So our largest perfect square that will factor into 320 is 64. Okay, is 64. All right, and lastly, what was the number we had? 567. 567. Let's find our perfect squares for 567. Okay, let's start by breaking it into prime numbers. Obviously, 2 will not go into it. Doesn't end with an even number. So let's try 3. Let's see, 5 plus 6 is what? 11. Plus 7 is 18. Will 3 go into 18? Then yes, 3 will go into this. If we pull out a calculator, we're going to find out it's 189 times. 3 times 189, because that's what we're doing here. We're multiplying these numbers. Will give us 567. 3 is prime. This number is not. I'll just go ahead and tell you. Let's see. 2 will not go into it. Does not end with an even number. How about 3? Let's see, because 3 is our next prime number. 1 plus 8 is 9. 9 plus 9 is 18. Will 3 go into 18? Yes, then it will go into that. How many times? Well, we may have to pull out a calculator, but it's 63 times. 63 is not prime. Will 3 go into that? 2 will not, because it doesn't end with an even number. So see, 6 plus 3 is 9, so 3 go into 9. Yes, so 3 will go into that. 21 times. And I think most of us see that that's 3 times 7. We're done with prime numbers. Do we have any pairs of prime numbers? Yeah, we got 2 3's there. We have 2 3's there. So we'll take those pairs and we'll multiply them together. 3 times 3 is 9. 3 times 3 is 9. 9 times 9 is 81. Now, alternatively, I didn't show you this way, but you could have done this. You could have just went 3 times 3 times 3 times 3, multiplied to 4 3's, and you'd have still got to 81. I think breaking it into parts is probably easier. 3 times 3 is 9, 3 times 3 is 9, and then we multiply those together to get to our largest perfect square that will go into those numbers. Okay. This tends to be, for a lot of students, one of those things that's really going to come back to you really quickly, or it isn't. Okay, there's no middle ground. Rewatch, back this up and rewatch it a couple times if you need to. But it's important for your better understanding, ease of understanding. We'll say it that way, of the idea of getting approximate solutions and actual solutions for radical type problems in your 155 course. You need to be able to identify largest perfect squares, okay, largest perfect squares that will go into numbers, because you'll use this information to then solve those types of radical problems. Okay? All righty. What else do we have? All right, so now we're on to reducing fractions. The rule is, and it's probably been mentioned a dozen times already, and it'll probably be mentioned a dozen times before we're done because it's so critical. And sometimes when things are mentioned, people aren't ready to hear them, if you understand what I'm saying. So that's why I oftentimes, and I've already made this statement before, so I oftentimes repeat the same thing over and over. It's not just to put you to the place where you say, okay, yeah, I've heard that before. It's the reality that some folks haven't. I may say something 20 times and some nobody will hear it because it wasn't important to them at that time. It's the 21st time that they finally go, oh yeah, I hear that now. They're ready to use it. So the reality is I've talked about the fact that when it comes to fractions, no matter how we get a solution, adding, subtracting, multiplying, dividing, we don't care. How we get to the solution is irrelevant. As long as our math is correct, we know we have a good solution. The overarching rule, in one of my math classes, I used to call it the big kahuna, the big one. The overarching rule in mathematics is we always reduce or we always simplify, another way of saying that, fractions to their lowest form. We always do so. The only time we don't do so is when we're told not to do so. So let's talk about how we reduce fractions. Well, a couple things we've already talked about, and I have some divisibility rules over here. How do we know the number 2 goes into a number? Well, it ends with an even number, so 2 will go into those two numbers. It'll go into that one. It'll go into those two numbers. Okay, so you'd probably start doing what we did on the previous slide. We could start breaking each of these into prime numbers, and that is one way to simplify fractions, using prime numbers, and then utilizing something called the greatest common factor process. We could determine the largest number that will divide into both the numerator and denominator in each case, divide them by that, and then simplify them to their smallest form. The rule of 3 I've alluded to. The rule of 3 will go, how do we know 3 will divide into a number? And oh, by the way, when it comes to simplifying fractions, that's what we're doing. We're dividing. Your fraction bar means divide. I've mentioned that before. Okay? And when you're simplifying, you're literally looking for numbers that will divide evenly into both. Okay? And if there's 5 numbers, you want to use the largest one. All right? That will go into both. Rule for 5 basically says if a number ends with 0 or 5, 5 will go into it. And the rule for 10 basically says, if a number ends with 0, 10 will go into it. And I've put these rules in your Math 013 course. It covers the rules for number 4, number 6, number 7, etc. Your 155 instructor may just tell you to use a calculator. I don't know. I'm not going to use this method or the GCF method. I'm going to use something called factors. I'm going to use a factor table. I think we've already seen it before, and if not, we will see it today, and we'll see it many more times before it's over. What are we talking about when it comes to simplifying fractions? What do we mean? Well, again, let's talk about the reality that when it comes to fractions, we can utilize literally an infinite set of numbers to show the same amount. And I'll just stop here. That right there is 5 different ways to say the same thing. That's the beauty. I respect a lot of us don't see the beauty maybe, but that's the beauty of fractions. We can use a multitude, an infinite set of values to represent the same amount. Each of those 5 ways are the 5 different ways, if you will, to say half of something. If you'll examine the numerator, the top number in each of those fractions I've written there, each of them is exactly half of the denominator, the bottom value. They all represent the same solution. So let's say we did some math and we came up with an answer of 4/8. We don't care how we got 4/8. We got it. It's the correct solution. Our math was correct. If we enter that as a solution, as a common practice, we're going to be told we're wrong, even though our math is correct, because the rule in fractions is you always reduce, you always simplify unless told otherwise. So how do we reduce fractions? Well, that's what we're about to go through. But basically, this one would be simplified to 1/2. 4 is half of 8, 1 is half of 2. Those are two different ways to say the same thing. You were given a half of something, you were given 4/8 of something. You'd quickly realize you have the same amount of whatever that something may happen to be. So that's what we're going to do here for each of these. And I just realized I may need an additional sheet of paper for these as well, so let me grab some. Basically, when we're simplifying fractions, we can use those divisibility rules. We can sit here and go, okay, 2 will divide into both, and we'll get an answer, and then we'll check and see if it will simplify again and again, etc. We can break them into prime numbers and use something called the greatest common factor process, which is beneficial if you're going into algebras, but if you're not, it's just esoteric. It's knowledge for knowledge's sake, if you will. But what we're going to do here, and I'll just use a sheet of paper here to the side, fraction bar means divide. Okay, your fraction bar means divide. So when you're simplifying fractions, you're looking for numbers that will divide evenly into both. My method, and you can use it always, it'll always work when it comes to simplifying fractions, whether you're doing it for a class like this, you're doing a quadratic equation, whatever, it will always work. Is it the only way we can use? No, I've already mentioned a couple. Greatest common factor process, divisibility rules. There are a multitude of ways, tools, if you will, that we can use to reduce fractions to their smallest form. What I'm going to do is I'm going to take the smallest number because it's the smallest number. No other reason. You could use a large number and the same thing would work. I'm going to make this little T-chart here. And I'm going to list the factors. I've already talked about what factors are. In fact, in math, factors are numbers that we multiply. 6 times 7 is 42. 6 and 7 will be called a factor. My factors of 140 are 1 times 140. I could go 2 times 70. Will 3 go into it? No, because if I add 1 plus 4 plus 0 together, I do not get a number that 3 will go into. It ends with an even number, so we know 5 will go into it. We can go 28. Okay, will 6 go into that? Well, we'll just use a calculator. I'm using the calculator off to the side here. 140 divided by 6. Yeah, it will, but not an even number of times. How about 7? Yeah, 7 times 20. That'll go into it. Anything else? Let's just look for laughs and giggles here. 140 divided by 8. No, it won't work. 140 divided by 9. No, it won't work. 140 divided by 10. Yeah, 10 times 14. And for argument's sake, let's just say that's it. Okay, this is for demonstration purposes anyway. Okay, so these are the numbers that will multiply / divide into 140. Well, any of those numbers also divide into 250 because what we've done is we found all the numbers that multiply and divide. These are our factors and our divisors of 140. All of these will go into 140. Well, any of them also divide evenly into 250. Well, if we break, I don't think we need a calculator, but let's just pretend we do. Okay, so our number is 250. So let's go 250 divided by 140. Okay, it will go into it, but not an even number of times. And what we do is we go down this way, and if we don't find anything, we turn the corner and go back up. Okay, so let's go 250 divided by 70. It'll go into it, but not an even number of times. 250 divided by 28. And I think most of us probably see the number that goes into both of them, but if not, don't worry. We're doing this for demonstration purposes to show you the process. Okay? All right, so let's go 250 divided by 20. Goes into it, but not evenly. 250 divided, oops, hit the right numbers, Rick. 250 divided by 14. Goes into it, but not evenly. 250 divided by 10. Ding, 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 ding. We have just found the largest number that will divide into both of them. So if we were to divide both of these here by 10, divide both by 10, what do we end up with? 140 divided by 10 is, I can get that out of the way for a second, is 14, and 250 divided by 10 is 25. We have just reduced that fraction to its smallest form. Okay, we have just reduced that fraction to its smallest form. And we'll do the same thing here for the next one. Okay, for the next one. All right, so again, I'll simply take, because it is the smallest number, I'll take the number 21. I'm going to take the number 21. I'm going to make a T-chart. What are the numbers, what are the factors I can multiply in the correct order to arrive at 21? Well, I can go 1 times 21 and 3 times 7. Those are our factors / divisors of 21. Well, any of those also divide evenly into 22. Well, let's check. Let's see. 22 divided by 21. No. Again, remember, we're going down this way. If we don't find anything, we'll turn the corner and go that way. Okay? So let's see, 22 divided by 7. No. How about 22 divided by 3? No. The only number in this case that will divide into both the numerator of 21 and the denominator of 22 is 1. And what happens when we divide both of those by 1? Okay, divide both of those by, I don't know why I put a plus sign there. Divide them by 1. Well, we end up with the same thing we already had, which is basically telling you this much. To verify that a number is already simplified, if the only number that will divide into both, well, you have verified that. Okay, so we basically verified this is already reduced to its smallest form. All right, let's do the next one here. Let's do 15 over 25. We're trying to reduce it. We're looking for numbers that will divide evenly into both, realizing our fraction bar means divide. I'm going to take the number 15 just because it's smaller. I'm going to list my factors of 15. What numbers can I multiply in the correct order to arrive at 15? Those are also my divisors. Well, any of those numbers also divide evenly into 25. Okay, so again, we're going to go this way. We'll turn the corner and go back that way. Well, let's look here. I know you can't see that. Let's bring it over here so we can see it. So 25 divided by 15. Well, it'll go into it, but not an even number of times. 25 divided by 5, ding, 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 ding. We have just found the largest number that will divide into both. Okay, so then we come over here and we divide both of them by 5. 15 divided by 5 is 3. 25 divided by 5 is 5. We have just simplified 15 over 25 to its smallest representation of itself. We have just simplified it to its smallest form. And then finally, we'll do 4,500 over 1,500. Okay, that's an improper fraction. It's a top-heavy fraction, but don't confuse improper with wrong. Improper fractions are just fine. They're fine solutions, okay, unless you're told to change it to a mixed number or some other form of itself. All right, so here I'm going to take 1,500. I'm going to list my prime numbers, or my factors. I'm hung up on prime numbers for some reason. I can go that. I could go 2 times 750. Let's see, 1 plus 5 is 6. 6 plus 0 is 6. Plus 0 is 6, so 3 will go into it. I could go 3 times 500. Will 4 go into that? We won't look for all the factors. We're just doing this for demonstration purposes. We'll look for a few of them. 1,500 divided by 4. 4 will go into it 375 times. We know 5 will go into it because it ends with an even number. 5 times 300. Let's just leave it at that. We'll leave it at that. We'll cut it down to size. And if we don't get it to the smallest form, we'll just do the whole process over. So you don't have to list 27 factors. I guess that's what I'm saying. You don't have to make 2 pages of factors. You can just quickly cut the numbers down to size, if you will, by looking for a number that will quickly divide into both. So all of these we've identified here will divide into 1,500. Will any of them divide also into 4,500? Again, we'll start this way, turn the corner. All right, so if we go, 4,500 is the number we're looking for. If we go 4,500 divided by 1,500, look at there. We have just that quick found the largest number that goes into both of them. 1,500 will divide into both of these. So if we divide both of these by 1,500, okay, 4,500 divided by 1,500 is what? It's 3. 1,500 divided by 1,500 is 1. So we'd say the answer is 3 over 1, or we could simply write that as 3 if we're allowed to do so in our problems. Remember, top number divided by bottom, 3 divided by 1 is 3. Okay, so that's what we're doing when we're reducing fractions. Are you going to be an expert after listening to me talk about it for 5 minutes and showing you 4 examples? I would hope so, but let's get in touch with reality. Probably not. Understand the idea. That's all you really want to know at this point. You're reducing fractions by looking for values that will divide evenly into both the top and bottom numbers. When the only number that will divide into both is 1, that tells you that fraction is already simplified. Okay? We can use the greatest common factor process, which I'm not going to demonstrate. We can use divisibility rules, or we can use those factor trees that I've been using. Okay, it's probably the best way once you grasp it. If you've never used it before, it can be a little cumbersome, but it is a very powerful tool that will always work. Okay, all right. Writing fractions as decimals. Writing fractions as decimals. When it comes to representations of numbers, 3 common ways to represent them are as fractions, are as decimals, and as percentages. Those are the most the most common ways you're going to see the same value represented. For example, if we had a fraction, and then we're going to turn it into a decimal, which we're going to practice with here. We could also turn it into, I'll just use a percent sign. Okay, and the method is this. If I had 1/2 of something, I can do what I'm about to show you here, which is take my top number, fraction bar means divide, and divide it by the bottom number. If I do that, that's going to pop out of my calculator, 5/10. Percentage means per 100, so the math involved here is by multiplying by 100. That would be 50%. So those three things, those three values there represent the exact same amount. So we can convert between each. We can change percentage to fraction, decimal to percentage, decimal to fraction, percentage to decimal, and vice versa. Okay, we can convert between all of them. Sometimes there's a need for answers in percentages. Sometimes decimals are preferred. Oftentimes fractions are preferred. So we need to be comfortable with conversion between each of them, and we'll get more into these different conversions as we move forward. So again, our fraction bar, let's revisit the reality. The fraction bar means divide. You know, back in the day, I love that term. Somebody showed you a fraction sign, but they probably never discussed, perhaps they never even thought about it themselves, or perhaps they never knew it themselves. Those are actually, we could argue they are, many people would argue against it. I don't know why, but those are variables. They're placeholders. Okay, so anytime we see a fraction bar, it means divide. And the math involved, any conversion is always top number divided by bottom. Okay, the way it's written in some math books, they'll have you think it's the other way around. And that's, again, most math books are written by people that were doing math before they were out of diapers in some cases. It just came natural to them. They didn't realize that 99% of the population, well, it didn't come natural. Okay, very smart people, but only to a point. Okay, only to a point. We've all heard of people who, you know, can't dress themselves, but they can play, you know, classical music. Okay, just without not ever seeing classical music, they're, you know, they can do that kind of stuff. So you can be very intelligent, but also not very intelligent at the same time, I guess is what I'm saying. Sadly, that happens a lot in mathematics. Okay. Anyway, how do we turn anything into a decimal? Well, it's top number divided by bottom. So here we would go 100 divided by 64, and that's what pops out of our calculator. Now, we're not told what to round to here, so we're just going to list all the factors because we'll talk more about rounding later on. 5625. Okay, what is that? Well, when we see the decimal, we say the word and a decimal is named by the position of the last number. Okay, so what position is that 5 in? Well, if you don't know, here's a neat little trick. Put down your number here. If it's a 10, if it's a 50, whatever. If you have 5 numbers in front of the decimal, just write a 1. And then how many numbers do we have after the decimal? We have 1, 2, 3, 4. 1, 2, 3, 4. What number is that? 10,000. So this would be 1 and 5,625 10,000ths. This number here, for our purposes, and that number there are the same amount. Now, there's 2 different ways to show the same thing. Okay? All right, let's go ahead and do this next one. Again, it'll be top number divided by bottom. So 1,150 divided by 1,400. And that's what we get in our calculator. Okay? Let's just go ahead and, let's just go ahead and put them all in. We'll put them all in. Shoot, it's not going to hurt us to put them all in. Ink and paper is cheap. So 0.8214285. And if you have a better calculator than my $2 calculator, you may have more numbers. Okay? Let's see if we can identify, though, because it's a good habit to get into. Now, I'll go ahead and tell you, we won't say the word and here because there's no value in front of the decimal. The 0 is basically representing nothing. Okay? So, but what we could do, again, is we could put a 1 there for the number or numbers to the left of the decimal, and then count how many numbers we have after the decimal. 1, 2, 3, 4, 5, 6, 7. We're going to have 7 zeros. 1, 2, 3, 4, 5, 6, 7. So what is that number? That is 10 million. So to correctly say this decimal here, we would say 8,214,285 10 millionths. We've got something that has 10 million total parts, and we're dealing with 8,214,285 of them. Wow. Okay. Let's do this one. Running out of room here. That's okay. Let's do this one. So we'll go 525 divided by 495. And we arrive at that. Now, if you notice there's a pattern there. 06, 06, 06 are repeating forever. Okay, 06, 06, 06 are repeating forever. But we'll just use what's on the calculator because we need some practice with properly naming this value. So 1.060606. And your calculator may have more digits. Okay, what is this number? Well, here we have a value in front of the decimal. So we'd use the word "and" for the decimal. And let's figure out what position that is in. We'll just take the 1, put it down. Again, if it were a 5 here, we'd still put a 1. If this was 27 point something, we'd still put a 1. Okay, that 1 is representing all values to the left of the decimal. Count your, how many numbers after the decimal? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, so 1 million. That number is in the 1 millionth position. That last digit's in the 1 millionth position. So to correctly say this, we would say 1 and 60,606 1 millionths. We've got something that has a million parts, and we're dealing with 60,606 of them. All right, last one here. Let's do this one. Okay, again, it's going to be top number divided by bottom. So we're going to go 56 divided by 168. Okay, so that's continuous threes. And again, we'll use them. 0.3333. How many threes do I have on there? 7? Yeah, it's close enough. Okay, so what would that name correctly be? We'll deal with rounding later. I think you see why we oftentimes round, because it's impractical to write out all these digits all the time. They're just not needed. Okay, for something called, and again, you may learn about this in your 155 class, you may not, the idea of accuracy and precision, if you will. Do you need to know all that? No, you don't. But what position is that last number in? Because again, the last number, the furthest right value that we have listed anyway, because these threes would continue forever. You know, the sun would burn out, the universe would come to an end, and we'd still have threes going on forever. That's how large this number is, or if you will, technically how small it is, because it's getting smaller and smaller. What number is that last 3 there in? Again, we'll just put a 1 down for any values to the left of that. How many numbers do we have here? 1, 2, 3, 4, 5, 6, 7. So 1, 2, 3, 4, 5, 6, 7. Okay. The grouping, if you don't know, you don't need to know this, the grouping of digits into 3 numbers like we commonly do, these are called periods. These are your ones periods, your thousands periods, your millions period will be Trivial Pursuit question there. So this is 10 million. That last 3 is in the 10 millionth position. So what would we say? Well, we'd say 3,333,333 10 millionths. We have something that has 10 million parts, and we're dealing with 3,333,333 of them. Okay? More than you bargained for there, but it's also some useful information. It cannot hurt you to know what I just told you. All right, and again, you've probably taken a break by now. If not, this might be a good time to take a break. We're going to switch gears and get into something new. We're going to solve equations using division. Now, what is an equation? Well, if it has an equal sign, it's an equation. It equates to something. It doesn't have an equal sign. Commonly in mathematics, we call it an expression, which is weird because we always find answers to expressions as well. So don't study on that too hard, okay? Just don't. Equation means it equates to something. We're looking for a solution. But oftentimes we'll say to evaluate an expression which doesn't have an equal sign, and we're also looking for a solution. So does it make sense? No, I don't think it was ever meant to. But anyway, I digress. With problems like this, okay, we've got variables. We have a placeholder. We have an unknown, yet to be named player, however you want to view a variable. When it comes to variables, the rule is in math it's straightforward. Once you know it, you know it. The rule is to isolate the variable, get the variable by itself. Common practice says to the left side of the equal sign. Does it matter? No. Sometimes on the right side you have negative variables. We don't like those, but there's a simple way to deal with those that you probably don't need to know for your 155 course. But the rule is to isolate the variable. Okay, so this is solving equations using division. So they're kind of telling you what the math is here. You're going to divide. I guess the question is, why are we dividing? Well, the rule is to isolate a variable, we need to remove the other values. And sometimes we'll use, we're going to be using, amazingly, what's called the multiplication principle here, even though we're dividing. Multiplication, division, mirror images of each other. Later on, we'll use what's called the addition principle, which is where we deal with the values that don't have variables. But the value in front of a variable, that's called your, again, I've talked about this a couple times, just the language of math, that's your coefficient. To solve each of these, we need to eliminate the coefficient. In every case, the coefficient is being multiplied times the variable. This is 16 times b, 5.6 times w, 7 times p, 2.5 times x. In every case, we're always going to do the opposite, so that's why they're telling us division. And that's how you isolate a variable. If you were adding a variable, to get it by itself, you would subtract, etc. You always do the opposite. Well, so we're going to use our fraction bar. Equal literally means balance. You've seen me talk about this before. You got a scale. The problem is currently balanced. If we don't do the same thing on both sides, it's no longer balanced. We're creating new problems. We're not solving a problem. So if we divide by 16 on one side, we do on the other. Simplistically, we just say these cancel out, in which case we're left with, I don't know how I put a 5 there. We're left with b is equal to, again, we know what this is, fraction bar. We know the math is always top number divided by bottom. So we would go 192 divided by 16, and our answer is 12. Just that quick, we found the solution. Okay, we found the solution. And that's how you solve all of these problems always. You isolate the variable. How do you isolate the variable? By doing the opposite of what's currently going on. In every case here, we're multiplying. So in every case, we're going to do the opposite. Both sides of the equal sign, because equal means balance. So this becomes W is equal to, okay, we're just going to use a calculator to solve these problems. 54.32 divided by 5.6. If we were doing this by hand, we'd have to do some conversion. 9.7. We'd have to do some conversion, because if we were doing this, I'll just go ahead and demonstrate it to you and show you what I'm talking about. We won't worry about it too much, but that's top number, 54.32 divided by 5.6. This number right here, number of the fraction bar, this number right here, or if we were doing it the traditional way, 54.32 divided by 5.6. 5.6 in every case is called your divisor, okay, language of math. Your divisor cannot be a decimal. So in this case right here, we'd have to move the decimal to the end, in which case we'd move it one time there as well. Just showing you that for demonstration purposes. All right, here we're going to divide by 7 on both sides. Again, we do the same thing on both sides of the equal sign. It cancels out there. Okay, so Lord have mercy, I'm just making things up. P is equal to, okay, let's do this, 91.5 divided by 7. It is that. Let's just go ahead and write it all down. We're not told to round here. We'll worry about the rules of rounding later, one thing at a time. Let's see, 1428. Okay, that's what that would be. And just for giggles, let's figure out what that number actually is. Okay, the number in the last position is the number that names it. We know when we see the decimal, there's a number to the left of the decimal other than 0. We say the word and. So here, let's figure out what that is. We'll just put down a 1 for all the numbers to the left. How many numbers do we have after it? 1, 2, 3, 4, 5, 6. So we'll put a 0 for each of those. That would be 1 million. So this would be 13 and 71,428 1/millionths. We have something that has a million parts, and we're dealing with 71,428 of them. Just added value there. All right, lastly, let's do this one. We'll divide both sides by 2.5. Again, we're always going to divide that coefficient out. That number with the variable is called the coefficient. On this side, we'll simply say it cancels. We're left with x is equal to, let's see, 0.45 divided by 2.5, and it gives us 0.18 or 1800ths. In every case, and let's go back and revisit. No, let's just leave it at that. Let's leave it at that. Let's leave it at that. I don't want to overload it with too much. Okay. All righty. And this is a demonstration of what we just did. This will be in the slides. You can pause and read this, help it make more sense. It's all written out exactly what we're doing, but I just showed you. In every case, though, we're isolating the variable by getting rid of the coefficient. We're dividing the coefficient out on both sides. That's it. Okay. All righty. Let's talk about some terms. Math is a language. A lot of us, and I think I've mentioned this before, and if I haven't, this is obviously it's the first time then. But I will mention it multiple times throughout the course. I've already talked about the idea of the number in front of a variable being a coefficient. It has a name. Everything has a name. 6 times 7 is 42. We already said 6 is called a factor, 7 is called a factor because we're multiplying. The answer is called the product. Math is a language. A lot of students are confused by that, but in reality, it's because of the language that a lot of students think they're not very good in math. The reality is most students that I've run across in my years of doing this are a lot better at math than they give themselves credit. They just don't speak the language. They don't parlez-vous mathe. So take the time to learn some basic terminology in math, and I think you'll be a lot happier because your instructor is going to use this terminology day in and day out, and there is an expectation that you understand some of the basic terminology. 4 of the most basic ones are here on this slide. I'm not going to do any writing at all. I'm just going to talk through it. Each of those terms means the answer. The answer is, okay? The answer is this. The answer is that. They all mean the same thing. So why do we use different words to mean the answer? And the reason is because we want to confuse you. No, we don't. Actually, we want to clear things up, okay? When I tell you the answer is 5 and I say the sum is 5, I don't have to show you the math. I'm just telling you, oh, by the way, we added some values to get to 5. 1 plus 4 is 5. The answer to addition is sum. So anytime somebody says a sum is something, you know they added to get there. Difference, well, when I tell you that the answer is, the difference is 7, I don't have to show you all the possible math I could have done to arrive at 7. I'm telling you that I subtracted to get to 7. So if I go, 9 minus 2 is 7, 7 is my difference. And I simply say the difference is 7, you know I subtracted to get there. Product. When I tell you the product is 42, I don't have to tell you the values that I use to arrive at 42. You know that I multiplied to get there. Product is the answer for multiplication. So if we were to go in that example we've already used a couple times, 6 times 7 is 42. 42 would be our product. By saying the product is 42, I'm telling the listener, you're being told as a listener that the solution was arrived at by multiplication. And lastly, quotient. Quotient is the answer for division. If I were to tell you that the quotient is 7, I don't have to tell you what numbers I divided. I'm simply telling you I used division to get there. I could have went 42 divided by 6 to arrive at 7. I could have used an infinite set of values, inclusive of decimals, to arrive at that same solution. I don't have to show you the math. I'm just by saying the quotient is something, I'm telling you the math involved was division. So take the time to learn these. Sum is the answer for addition. I said I wasn't going to write, but I guess I lied to myself. Difference is the answer for subtraction. Product is the answer for multiplication. And quotient is the answer for division. Okay? Take the time to learn those. It will help. You probably already know them. Like I say, math is use or lose. So you may have forgotten. Maybe a little rusty. All right, let's define real numbers. What are real numbers? Well, there are a couple, 2, 3 major categories. Some folks will say more, some will say less. We don't care at this point for our purposes. We do care, but not at this point in history. Where we are right now, we don't. In this course, anyway. The major category of numbers that we deal with on a daily basis, we call those real numbers. What is a real number? Well, it's any number you think of. Positive values, negative values, fractions, decimals, non-fractional, non-decimal numbers. Any number that you can think of would be called a real number. If you will, real numbers is a large storage cabinet that all your other numbers fit into. There are 2 sections, if you will, to that storage locker that you're putting real numbers into. There is a section that includes our rational numbers, and there's a section that includes our irrational numbers. And oh, by the way, when it comes to rational and irrational numbers, they are like oil and water. They don't mix well together, okay? They just don't go good together. A rational number will never at the same time be an irrational number, and vice versa, okay? What makes a number irrational excludes it from being back up and try that again. What makes a number irrational automatically excludes it from being a rational number. and vice versa. What makes a number rational automatically excludes it from being an irrational number. But inclusive of all of our irrational numbers and rational numbers, we get real numbers, okay? In our rational number category, we can subdivide rational numbers into many different categories. It's not on this list, but a common one that we commonly start with is what are called counting or natural numbers. In my day, they were called counting numbers, whatever that means. Today, we're talking more about them as being natural numbers. Counting and natural numbers mean the same thing. Okay, it's just two different words to say the same thing. What are those? Well, those are numbers like 1, 2, and 3. Those are naturally occurring things. 1 tree, 2 tree, 3 tree. We can talk about there being no tree there, but we couldn't touch it. So if you will, these are things that have form. We could give form to them or visualize them as having form. Those would be your natural or counting numbers. Start with 1, 2, 3, go on to infinity. No fractions, no decimals, no zero, no negative. What are whole numbers? Well, whole numbers are your natural numbers plus 0, going on forever. No fractions, no decimals, no negative values, okay? In this case, we see that numbers, we'll just pick on the number 3, the number 3 can be both a natural or counting number as well as a whole number. It can have two different names, okay? It has its given name and then it has a nickname, okay? And then we have integers. What are integers? Well, we take integers, we take all of our whole numbers, and then we also list their opposites, okay? No fractions, no decimals. Those would be your integers. So again, in our demonstration, the number 3 could be a natural or counting number, depending on when you learn to define them. It can be a whole number, and it can also be an integer. To this point, we haven't touched on fractions and decimals. Most of our fractions and decimals are over here in the irrational column. Not all of them, but most of them, okay? What is a rational number? Well, a rational number is where we start to bring out our fractions and decimals. And the fractions and decimals that do not qualify as rational numbers by default are irrational numbers. So I'm really just going to show you the definition of rational numbers, because if a number doesn't fit the definition of a rational number, it's irrational. The definition of rational numbers, there's really two of them. And your math books out there will talk about something in terms of ratios. But if you don't know what a ratio is, or ratios always, seem to stump you, knowing to use that definition can be cumbersome when it comes to defining what a rational number is. I use a very simplistic definition. The first definition, there's two definitions of a rational number. It is simply a number you can write down. 4. I can put my pen down. That's a rational number. It makes sense. It's rational. 1/2. I may have to convert that into a decimal. We know how to do that now. Top number divided by bottom, 0.5. But in either case, it's that. Oh, by the way, I can write that down as well. If you find yourself being able to write a number down, whether it's positive, negative, fractional, decimal format, if there is a simplified solution to it that you can write down, 2 digits, 57 digits, and place your pen down, by definition, that's a rational number, okay? The second definition of a rational number seems to go counter to the first one, okay, because this is where we'd have some number like this, okay, 1.273737373. I think we see the pattern there. That number is continuing on forever. So could we write it down? A lot of us would say no, but we actually have a system for writing that type of number down. We could do this. We could put the numbers that are repeating under a bar. Have we placed our pen down? Yes, we have. That's a rational number as well. So a repeating pattern number would be considered a rational number. So 1.333, 2.777, etc. Those are rational numbers. We have a system in every case for writing these numbers. We could do that. We could do that, okay? We're telling the observer that the value or values, as we saw here, under the bar are repeating forever. Have we written it down? Yes, it's rational. So what is an irrational number? Well, an irrational number is something like pi. 3's today, 3.1415923, I think it is. I'm probably wrong on one digit up there. Goes on forever. There's no discernible pattern. If we were to do the square roots of some numbers, let's do the square root of 2. Square root of 2, what do we get? Well, let's write that down and see why that's an irrational number. You know, square root of 2, the root of 2 is 1.4142135. You know, we just got done talking about perfect squares. Okay, let's do one of those. 100. You know, if we do the root of 100, we get 10. Okay? Well, roots and their squares are opposites of each other. Okay? Kind of like adding and subtracting, multiplying, or dividing and multiplying. Okay? They're opposites of each other. You know, if we were to do 10 to the second, we'd get 100. We'd get back to where we started. So they're opposites of each other. But here, and this is just a demonstration to show you why numbers like this are irrational. If you were to square that number, okay, let's square that number. I don't care if you got this many digits or 90 million digits after the 1. If you were to square that number, or take it to the second power. We already squared it, got to this number. So let's go 1.4142135, and then times 1 point, this is a cheap calculator, I have to do it this way, 4142135. The expectation is we should be able to get back to the number we started with, as we did with our perfect square of 10. 10 squared is 100 squared is 10, and then if we square it, we get back to 100. Okay, so they're opposite ends of each other. Well, here we did the square root of 2, got this. If we multiply it times itself, look what we get back to. We never get back to 2. We're never going to get back to 2. Okay, the closest we're going to get is an infinite set of 9s. Okay, we're never going to get back to it. Is that an oversimplistic explanation of what an irrational number is? Yes. Okay, it is. Okay, it's not meant to be complicated. It's not meant to dig under the hood and say, well, this always rounds to 1 or something like that. It's a demonstration of the fact that irrational numbers don't make sense. Okay, they do not terminate. There's no discernible pattern, whereas rational numbers do have a reality where we can simply write them down, or we have a system for writing them down. Okay, so those are your numbers. Let's take and let's identify each of these numbers here as either being rational, irrational, or real, etc. So we've already shown that the square root of 2 is an irrational number, but you know what? It fits in that big storage chest. It is also a real number. 2.576, is it a whole number? Well, whole numbers do not include decimals or fractions, so no. Is it an integer? Well, do not include decimals or fractions, no. Is it a rational number? Have we been able to write it down? We have, so therefore it cannot be both, okay, but it is also a real number. Minus 12, okay, or negative 12, whatever makes you happy. Is it a whole number? Well, whole numbers do not include negative values. No. Is it an integer? Well, integers are where your negative values come into play. No fractions, no decimals. Is it a rational number? Yes, we can write it down. So therefore, that precludes it from being an irrational number. Is it a real number? Yes, it is. The number 8, is that a whole number? Well, what are your whole numbers? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 to infinity. No fractions, no decimals, no negative values. So it is a whole number. Is it an integer? Well, it's also an integer, because what's an integer? An integer is all of your whole numbers and their opposites. Okay, so that would be an integer. Is it a rational number? Yes, which precludes it from being irrational, and it's also a real number. 3/11ths, is that a whole number? Well, whole numbers do not include fractions or decimals. No, it is not a whole number. Is it an integer? No, integers do not include fractions or decimals. Is it a rational number? Yes, we can write it down. Okay, well, let's see. Does that terminate? Let's say 3 divided by 11. Okay, what's going on there? The 27 is repeating forever, right? So we could actually write this down. This could be written as 0.27, put a bar over it. So it is a rational number and is also a real number. And lastly, we have this number here. We see the 2,1 is repeating forever. Okay, is that a whole number? Whole numbers do not include fractions or decimals, so no. Is it an integer? No, do not include fractions or decimals. Do we have a system for writing it down? Yes, and it is also a real number. Okay? All right. All right, now we're going to get into rounding rules. That's one of the reasons I didn't do rounding to this point, because I knew these were coming. Okay? Rounding rules. Historically in mathematics, teaching the level of math that I've been teaching for years, dabbling in algebra and stuff, but historically, there's 3 reasons that students struggle in math. Number 1, by any stretch of the imagination, is fractions. Number 2 is order of operations. This always pops up as number 3. This is the third reason students struggle in math, because we don't understand the rules for rounding. I've written them all down here so you can pause on this slide, and then we'll do some examples on the next slide, and we'll be done with this video. So what are the rounding rules? The value being rounded will either stay the same or increase by 1 digit. So the number that we're going to round, and we'll identify how to find that digit here on the next slide, is either going to stay the same. So let's just say we found the number 5. 5 is either going to stay 5 or it's going to become 6. That's it when it comes to rounding. Now don't confuse rounding with rounding up. That's something different. We'll demonstrate later. Okay? The value being rounded will either stay the same or increase by 1 digit. So if 5 is our number that we're rounding, we'll just arbitrarily say it's the number 5. 5 is either going to stay 5 or become 6. That's it. And how do we make the determination as to what to do with that value? How do we make the determination what to do with our 5? Keep it as 5 or keep it as 6? And the rule is we use the value to the immediate right of the number being rounded to determine what is done to the number being rounded. Read that sentence 3 times. A lot of rounded there. Okay? The number to the immediate right, even if it's behind a decimal, say our 5 is in the 1 place, the number to its immediate right, even if it's behind the decimal, is going to tell us what to do with our number. Okay? If there is no number there, we imply. That's a word we use a lot in math. It means pretend. We pretend there's a 0 there. Okay? So we put a number there, even if there is none. And then we use that number to the right of our number to make our determination to, as to what we do with our number we're rounding. And the rules are simple. You know these rules. You've used them before, but you may have forgotten. If that number is 4 or less, 4, 3, 2, 1, 0, count them. That's 5 numbers. 4, 3, 2, 1, 0. If the number to the right of our number is 4 or less, then the number we're rounding will stay the same. It will not change. Whereas if the number is 5 or greater, 5, 6, 7, 8, 9. Again, 5 numbers. Count them if you need to. The number being rounded goes up by 1 digit. Okay, so those are the rules. Find the number. It's either going to it's going to stay the same if the number to the right of it is 4 or less. It's going to go up by 1 digit if the number to the right of it is 5 or greater. So let's look at a couple examples here. We're being asked to round these values to different numbers. Okay, I have our rules up here again. Okay, to help us remember. So we're going to round to the hundredths place. And oftentimes we struggle with identifying what number's in the hundredths place. So here's a trick. And some tricks are good. And ones I'm going to show you are mostly good. Okay? Let's write down 100. How many zeros in 100? Well, of course, there's 2. So that tells us we're coming over to the second number after the decimal. And we know it's after the decimal because that word ends with THS. THS is to the right of the decimal. No THS, as we see here in number 3, is to the left of the decimal. Okay? We're coming over here. So the number we're rounding is 2. And basically we know that 2 is either going to stay 2 or become 3. What we do with it's determined by the number to the immediate right. And in this case, the number to the immediate right, I can talk, is 5 or greater. So our 2 is going to become 3. So this is going to round off to be approximately, we'll see the little wiggly equal signs, approximately 78.43, or again, if we were to say this out loud, we say the word "and" for the decimal. We know that 3 is in the hundredths position, so that would be 78 and 43 hundredths. 78 and 43 hundredths. Let's move on to number 2. We're going to round this to the tenths place. Again, we have the THS, which tells us it's to the right of the decimal. What number are we dealing with? Well, let's write the number 10 down. How many zeros? 1. So that tells us to go to the first decimal to the right of the decimal point. So the 5 is the number we're rounding. And again, when we're rounding, there's only 2 options. The number we're rounding, here 5, will stay 5, or it will round up to the next higher number, which is 6. And what we do with it's always determined by the value to the immediate right. Here in this case, it fits the rule of being 4 or less, and if it's 4 or less, it tells us the number we're rounding is going to stay the same. So this will be 12, approximately 12 and 5/10. Lastly, we're being told to round to the ones place. We don't have THS, so that's dealing with what? It's dealing with the first number here. It's dealing with the 7. That 7's in the ones position. Okay, we always look at the number to the immediate right. Yes, this here is behind the decimal, but we always look at the number to the immediate right to tell us what to do with our value that we're rounding. Okay, 7 is either going to stay 7 or become 8. That's it. No other options. we look at the number to the immediate right, in this case, it is 5 or greater, so that tells us to round that up. So our rounded solution here, our approximate solution, is 128. A lot of stuff in this video, a lot of good stuff in this video. Again, as I mentioned at the beginning, you should always try to watch these videos before participating in your 155 course, because the entire purpose of this course is to close that skill gap, if you will, between where a lot of you had tested and where you were placed into your 155 course. So make sure you try to view these weekly videos before you do the 155 course. All righty, thanks.